now we will demonstrate how you do the experiment. Okay. So the experiment is very simple. So let me turn on all the devices first. So this is the CRO. So I'm turning on the CRO first. So now this is expecting signals from X and Y, but there are no signals, so it's giving you a horizontal one. Okay. So what you can do, you can also shift it up and down. Middle. Then you have to turn on something called an XY mode. So you can see this XY button here. You have to turn that on. Okay. So you turn that on. So what does this? What it does here? It basically combines the X and Y signals and creates one. It adds them together and then creates one signal. Okay. So if you remember in your +2 you must have studied those figures. So this is just like that. Okay. All right. So now my CRO is on. I will turn on my control unit. Okay. Control unit for the ESR circuit. So let me turn it on. This is the main power button. So now you see it has been turned on. Okay. Now I have no current. You can see there is zero current which is showing. Okay. So that means there are no current to this coil. So there is no magnetic field. Okay. But it is still giving you some signal. So you can see the signal here. Okay. And it is in XY mode signal. Okay. So it's combined the two signals. So now, first of all, what you see is that it was a dot, right, before? Because there were no signals or anything coming in. Now there is a signal, but there is no magnetic field. So instead of a dot, you are now seeing a line. Okay. So you can now change the sensitivity of the CRO by using these two knobs. So channel 1 is getting signals from Y, from the Y. Okay. Channel 2 is getting signals. Channel 2 is this one. So it is getting signal from the X of the control unit. Okay. So, and this is the button for channel 1, this is the button for channel 2. So let me change channel 2 for example. See, now I am changing the sensitivity. That means if you keep an eye here, you will see the number of divisions per volt, or what is the equivalent in volt of 1 centimeter box. So that is being shown here. So 1 volt means 1 centimeter is equal to 1 volt along the X direction. Y has what? Y has 1 centimeter equal to 0.1 volt. Okay. So you can change both as per our needs. Now let's change the X so that if you keep on making it more sensitive, so the length increases, right? So you have to make it less sensitive so you can see the entire signal within the screen. So now you see a finite length is there, you can measure the length. So this measurement from here to this end, this gives you the P, the part P. Okay. So you have to refer to your manual to see the calculations and what are the data that you need to record. So once you refer there, you will understand what is P. So from this length, you will get P. Okay. So whatever is the length, you convert it into volt, equivalent volt using this sensitivity. So it now it is at 2 volts. That means 1 centimeter here is 2 volts. Okay. Along the X direction. So this gives you P. So fine. But we still do not have any magnetic field here. Okay. So yeah, this is still before applying any magnetic field. Now let's turn on the magnetic field. You see this button here, this controls current to the Helmholtz coil. So if I turn on the current, there will be something there, right? So let me turn on the current. Now you see the I have turned on the coils, but still the current is at 0 because I have this controller here which controls the current. So the ammeter is still showing 0 current and the signal has not also changed. Okay. So now let me give some current into it. Okay. So the lowest current that I give is this one. Okay. So usually you will not see the signals like this, so it will be some sort of a randomized kind of a signal, it will be a little bit noisy. Okay. So it will look something like this. So you see now there are 4 peaks that you are seeing. Okay. Again refer to the manual to understand why there are 4 peaks. Okay. What are these peaks? So basically the idea is whenever you have resonance, whenever the frequency to this tinier coil here, that is near the sample, whenever that frequency is equal to the Larmor frequency that comes from this magnetic field from the Helmholtz coil, whenever the two frequencies match, you get resonance and you get a peak here, okay, in the signal. So now suppose this is a resonance condition. Okay. Now from this frequency meter you can see a particular frequency. Okay. Now this control unit is not that efficient, it's not that expensive. So it's a small setup for lab experience. But the ones that you will get in research labs, they are much more extensive. Okay, so you can change the frequency over very large ranges. Here you can only change it somewhere between 13 point something to 16 megahertz. Okay, a very small range. So let me adjust the frequency knob, and you will see there is some change in the signal, but the frequency condition, we are not going very far away from the frequency condition. You see, it's 12.4 or 12.1 is the minimum. Okay. So let me go again to the maximum side. Okay. You have to do it slowly because it's very sensitive. So let me make it maximum. You see 15.7 or 16.7. Okay. 16.7. So this is the maximum frequency. We are still near the resonance conditions. You see, we are still seeing the peak. So we are still not very far away from the resonance condition. So within this 12 point something to 16 point something is your resonant frequency. So how do you identify that resonant frequency? We'll go into it. But first we need to do a bit of adjustment. So we will use a phase change setup, a phase change circuit that is inbuilt in the system. Okay. So what is phase change? Why is it there? You will again read it in the manual. Okay. So let me change the phase so that my peaks are the same X position. Now I have separate 4 peaks. I want basically 2 peaks. Okay. So I want to superimpose 2 of them with each other. Okay. So let me see. Let me change the phase. You see the peaks are moving away. If I do move in the opposite direction, the peaks are moving towards each other. Right. Now you see 2 of the peaks have coincided with each other. Basically the X position, the peak position is coincided, right? But you can still make out there are 4 peaks. So this is the role of the phase button. So this is basically, these are basically fine tuning your signal. Okay. So you already have a signal, you already can do a lot of things here, but you want to make it fine, more controlled. Okay. So now the role of the phase shifter is done. So now we will change the frequency to identify what is the exact position within this range, 12 to 16. Within this range, what is the exact resonance position? So what we will see if I keep changing the frequency, what is happening is that the peak heights are changing. Okay. So at some point you see the peaks will sort of superimpose with each other. Okay. And you will have only 2 peaks. So it is not working perfectly, but you see, wherever you see, wherever you are getting the best results, and you are almost seeing like 2 peaks and they are almost superimposed with each other. So that is the best possible setting for the frequency. That means that is the most accurate value for the resonant frequency that this setup can give. Okay. If you have a better, more expensive setup, that will work better. Okay. So in this experiment, 15.3 turns out to be the resonant frequency. You might get slightly different values. Okay. Now you do what? Now I have this current. Okay. I have measured earlier P. Now I have to measure the separation between the peak positions. That will give me something called 2Q. Okay. So again, refer to the manual to see what is the role of this 2Q quantity. So by measuring the difference between the 2 peak positions, I will get my 2Q value. Okay. So for this particular current, 100 milliamps, you see, this is one peak's position, this is another peak's position. Okay. So if you want, you can shift it up and down and bring it near the scale. Okay. So now you see, now you can count how many divisions are there in the X direction between the 2 peak positions, and then use this calibration here, or the sensitivity of the CRO, convert it into the voltage signal that is coming from the coil, that inductor coil that is there around the sample, small inductor coil. Okay, or the sensor. So this gives you 2Q. Now what you next do is, if I keep on changing the currents, you see the magnetic field of the Helmholtz coil will change, the resonance condition will sort of differ a little bit. Okay. So that means my peak positions will shift. So again you see, if I keep on changing, the peaks are coming closer together. I am increasing the current, in each step you see the current is increasing and the peaks are coming closer together. Okay. So at each value for current, you will measure the 2Q from this. Again you see, again if I increase it, it has come further again. Again you can shift in the y direction using the CRO and have an accurate measurement for the peak positions here. Okay. Again you see you are moving slightly away from the resonance condition because the peaks are separating out. Anyway, so we will do this experiment till we get all the different values for current and all the different values for Q. Towards the high values, there will be very small changes, so you have to be very careful. You can also adjust the phase if you want to. Okay. So that's how you measure what is to be measured here. Okay. Once you are done with this measurement, then you will refer to the manuals and the notes and to do the calculations and eventually figure out what is the G value. Okay. And this G factor. So once you know the G value, you can actually calculate what is the spin quantum number or what is the angular quantum number for the electron. Okay. So that is the role of the experiment. Okay. Angular quantum number of the electron in that particular sample. Okay. So Thank you for listening.